Welcome to the Explainer. Today we are taking a completely mind-bending journey into a totally different kind of mathematical universe. We're going to explore a space that looks and behaves fundamentally differently from the world we experience every single day, and it's all rooted in the incredibly elegant world of differential geometry. So, I want you to really think about this for a second. What actually happens when you break the absolute oldest, most foundational rule in mathematics? I mean, for thousands of years, our intuitive understanding of space was that it was just completely flat, perfectly governed by the rules laid out by the ancient Greek mathematician Euclid. But what if the lens we've been looking through all this time was just one of many? When mathematicians finally dared to challenge those ancient rules back in the 19th century, it was nothing short of revolutionary. As David Hilbert, literally one of the absolute greatest mathematical minds of the 20th century, put it, the discovery of non-Euclidean geometry was, quote, one of the most suggestive and notable achievements of the last century. It didn't just change math, it profoundly shifted our entire understanding of what geometry actually is. Okay, let's dive into this. Here is our roadmap for today's conceptual math journey. First, breaking Euclid's golden rule. Second, the weirdness of hyperbolic triangles. Then we'll examine three distinct ways to visualize this space: the upper half-plane, the Poincare disk, and the Beltrami-Klein model. Let's start with Section 1, Breaking Euclid's Rule. We're going to look at the fundamental assumption that held classical geometry together for centuries and see exactly how it was shattered. So, in standard, everyday Euclidean geometry, we have the famous parallel axiom. It basically says that if you have a straight line and a point just floating off that line, there is exactly one parallel line you can draw through that point that will never touch the first line. Just one. That's it. But look at the right side of our comparison here. In hyperbolic space, this rule completely breaks down. If you have a line and a point not on it, there are literally infinitely many straight lines passing through that point that will never ever intersect the original line. No way, right? But it's true. Which brings us to Section 2, the weirdness of hyperbolic triangles. Breaking that parallel axiom isn't just a neat little party trick. It fundamentally distorts the reality of basic shapes. In our standard Euclidean world, you know that the inside angles of any triangle always add up to exactly 180 degrees. But in hyperbolic space, the angles of a triangle always sum to less than 180 degrees, every single time. And here is where it gets really weird. In flat space, you can have a tiny triangle and a massive triangle with the exact same angles, right? They're just scaled versions of each other. But in hyperbolic geometry, similar triangles are always perfectly congruent. If two triangles have the same angles, they absolutely must be the exact same size. It all boils down to this really fascinating formula. In hyperbolic space, the area of a polygon is dictated purely by its angles. For a triangle, the area is simply pi minus the sum of its internal angles. Because of this totally unique geometry, a triangle's area actually dictates its exact size. That means you cannot shrink or grow a shape without fundamentally altering its angles. Geometry and size are inextricably locked together like a giant puzzle. Let's move on to Section 3, the upper half-plane model. Because hyperbolic space is so incredibly abstract, we need specific visual lenses to actually map it onto our flat screens and paper. Now, what's really interesting about this slide is how a straight line actually looks here. In this model, the entire universe is mapped onto the top half of a standard graph. The boundary of the whole universe is that horizontal real axis at the bottom. In this space, the shortest path between 2 points, the straight lines, or what mathematicians call geodesics, are actually sweeping semicircles whose centers lie perfectly on that bottom axis. Or if the line goes straight up, it just looks like a vertical half-line. Now, you might be thinking, those look completely bent. How on earth is that a real geometry? Well, the upper half-plane is what we call a conformal model. This is a crucial concept. It means that even though the lines appear heavily curved to our flat space eyes, the angles where any two lines intersect on this page perfectly match the true hyperbolic angles. The angles are completely accurate, even if the distances look totally distorted to us. All right, let's look at another way to visualize this in Section 4, the Poincaré disk model. While the upper half-plane stretches out to infinity upwards, this one takes a wildly different approach. Brings us to a seriously mind-bending classification: ultra-parallel lines. These are lines that diverge so dramatically they don't even meet at the boundary at infinity. And they have this absolutely fascinating geometric property. Any two ultra-parallel lines will always share one and exactly one unique common perpendicular line that cuts straight across both of them at perfect 90-degree angles. Let's move to our final section and see how this builds into one last highly unique lens: the Beltrami-Klein model. This one actually prioritizes straightness. Well, you don't get something for nothing in differential geometry. There's always a catch. And this brings us to the Beltrami-Klein trade-off. Because we intentionally forced the mapping to make the lines look completely straight, we basically had to stretch and warp the angles to do it. This model is not conformal. A 90-degree intersection in true hyperbolic space is not going to look like 90 degrees on this particular disk. So let's just quickly summarize these three amazing models. The upper half-plane uses semicircles and keeps the angles accurate. The Poincare disk packs the whole thing into a circle with orthogonal arcs, also keeping angles perfectly accurate. And then the Beltrami-Klein model gives us those visually straight chords, but it sacrifices the true angles to make it happen. It's absolutely vital to remember that none of these models are the true shape of hyperbolic space. They're just different mathematical lenses, different flat translations of the exact same bizarre, beautiful geometry. Which leaves us with a rather profound thought to end on today. We've seen how rules we thought were universal and unbreakable can totally be broken, and how straight lines and shapes change entirely depending on the curvature of the space itself. So, if straight lines are really just a matter of perspective and mathematical modeling, what shape is the universe you are sitting in right now? Are we truly in a flat space, or are we simply looking through the wrong lens?